Well, aloha and welcome to a special screencast of session 3 on the second part of inventory management. We'll be talking about extending the basic idea of inventory management in terms of keeping stock on hand and when to reorder by looking at uncertainty. So at this point, we've only talked about inventory management for which everything was deterministic, and that the demand, meaning that the demand was always constant, that we only had 5 beers a day and we always drank 5 beers a day, and that didn't change. We also assumed that there was no lead time, or that if there was a lead time, the lead time was constant. Once again, no uncertainty at all. But more realistically, demand is not certain, as we looked at with the news vendor model. And lead times, for which how long it takes to replenish something in your inventory, also tend not to be constant. So we're going to relax some of those assumptions that we made to get a little bit more realistic model and look at those different applications. You may wish to have the in-class exercises handy as you look at this, because there'll be points in the slides where I'll indicate which material that we're looking at corresponds to which problem, and so that since it's fresh at hand, you can kind of take a look at that and see how it would apply. I might indicate a few notes as we go along. So let's dive into the world of uncertainty in inventory management. Now, previously we had discussed the demand for our goods as depleting our inventory at a constant rate. And so that was indicated kind of by a line that was stretching, a decreasing line, and that over a period of time here, our inventory levels would decrease based on at a constant rate D, what we call the demand. Now we're going to imagine that that rate D is not constant and it will vary, and so we'll have this sort of curvy line here that sometimes we'll have not so much demand, and then sometimes we'll have a little more demand, maybe a little less demand, etc. Of course, there'll always be what we expect as kind of an average demand or expected demand, and that will be represented, of course, by a constant line. There's going to be a constant average demand. So the idea of what is the effect of having variability of demand? Well, the effect is that we cannot predict exactly what time, when we're going to run out. So if this line here represents zero inventory, the effect of variable demand means that we won't know exactly how long it'll take. In other words, how long in this direction here, in this axis, it'll take for us to reach this point. We'll certainly know on average how much it takes, but we won't know exactly. So the idea is that we're going to need to hedge against that by trying to anticipate the variability in the demand and keeping additional stock levels on hand to make sure that we always have stock on hand through a period of time, which we'll call the lead time. So this lead time here is that we'll place an order, and that order will take a certain amount of time to come in, and between that time period we want to make sure that we have enough stock on hand to service our customers, or enough in inventory, I should say, to service our customers. Of course, during that lead time, we can only know we won't know exactly what demand is. We'll only know what the expected or average demand is. So what we'll call that time period, this time period L here is the lead time. It's the time period between placing an order and then receiving that order. We want to make sure that we don't run out of stock during the lead time. And the amount of stock that we'll keep on hand over that lead time is going to be called the base stock level. So the base stock level is, again, the amount of stock that we keep in inventory over the lead time. That's opposed to the actual stock level, which of course, as we know, will just be decreasing over time. The main question again is, how much inventory do we need to keep in the base over the time L to hedge against this uncertain demand so that we don't run out? The problem, of course, is that if we order too much at the order time, or have too much at a certain time, then by the time we get to the order point, that we'll end up having too many, and we'll have an amount that's left over. Instead of running out of inventory and then replenishing it, we'll have an overstock, and that overstock will be subject to overage costs. Similarly, of course, if we have too little at the order point, then we will run out before the lead time is over and we replenish our stock, and will be subject to a shortage or have an underage, both of which of course are not particularly helpful. So how much do we want to hedge is the question. Well, of course, this is very similar to our usual newsender problem, that we have overages and underages, and we want to balance out the costs associated with that. So the base stock S is what we'll define again as how much stock we carry over the lead time, or what the reorder point is. In other words, when we get to that level, we need to reorder because we need to make sure we have enough at that point to carry us through the lead time for which we will be replenished. So again, the base stock S, the little s we'll call it, is the stock carried over the lead time, or sometimes called the reorder point. We're going to assume that the demand over the lead time is a random variable, just like the demand is variable or uncertain, as in the news vendor problem. We're going to assume again that we don't know exactly what it is. Typically, we will assume by abuse again that the distribution of the demand is normally distributed. If we don't know what it is, it's usually a pretty reasonable thing, but technically it's not really correct to use the normal distribution, but frequently we get away with it. Sometimes they will also use the uniform distribution if we really want to assume maximum uncertainty over a fixed interval. Fixed interval meaning a fixed amount of stock that we can carry. It's going to be between 0 and some number. And again, for technical reasons, that would be, we would assume the uniform, or at everything is equally probable, whereas the normal distribution, the things towards the mean are more probable than things away from the mean. So how do you calculate such base stock when you have mismatched stocks? Well, you could do the same thing, except for we have our critical ratio for the news vendor, where we have the optimal quantity Q. That, in other words, the probability for the optimal amount was going to be equal to the critical ratio, or the underage cost divided by the sum of the underage and the overages. And then what we did to figure out Q is we looked at the inverse distribution. So this would be the probability that demand is less than Q, that we run out. And we found that this was the balance point. And so if it was normally distributed, we'd look at the inverse normal to find out what value of Q gives this value for a probability. Well, this is the same thing, except for instead of looking at over the entire inventory time period, we'll just look at it over the lead time. So if we look at the S as the base stock we want to figure out, right? We can look at the underage and overages for not having enough or having too much over the lead time. That's over the lead time L. And once again, given the probability distribution, say it's normally distributed, we just look at the inverse of that to find out what value of S gives that probability. So it's pretty much the same thing, except we look at over the lead time instead of over the entire time. So the formula, of course, will be the same thing. If we know what the safety factor is, and the mean demand and the standard deviation over the lead time, that is, not over the whole time, but over the lead time, then we can figure out what base level S to hold that would give us the probability that the demand won't run out, or at least the optimal one. So again, base stock level, the mean time over the mean demand over the lead time. So we're going to actually call that AVGL, or average lead. And you'll see that since it's over the lead time, it's not a single day. It's over the number of days, weeks, or whatever it is that the lead time is in. And then similarly, we still have the safety factor, which we would usually look up from a table or inverse normal or something like that. And then we have the standard deviation of the lead time, again, over the lead time, which is going to be a little tricky because it's not going to be the same as the standard deviation of the demand. It's going to be the demand compounded over the lead time. Just like the mean over the lead time will be compounded over the number of days, the variability will also change. In fact, it'll increase over the lead time. I'll get onto that a little bit later. We also will use the notation STDL, or standard deviation for the lead, to represent that when we're talking about the base stock level, little s. What the average amount to hold over the lead time, or AVGL, is going to be called the pipeline inventory, or the on order inventory. You'll see that will become more apparent why. That's sort of how much we have in the pipeline, you'll see, or how much we're going to have shoveling through our inventory. And then this is going to be the safety stock. In other words, this is how much we vary on average. This is going to be the safety factor for which we proportionally increase or decrease the amount that we hold in our pipeline to match a certain optimal amount or a service level that we're looking for. So again, what does S signify? So let's again assume that, let's just make it simple, and we'll take that the demand during the lead time is independent and identically normally distributed. This is very important because we'll find out that, without such assumptions, it makes it very difficult to calculate or estimate what some of these things are. So normally distributed, we know, we're just going to assume that the value of the demand over the lead time is bell-shaped. Independent and identically normally distributed seems to mean that as demand is done over the lead time, that every day that demand is, say, made, that it's normally distributed with the same mean and standard deviation. And independent means that one day does not depend on the next. There's no relationship between one day and another day. That the demand is not affected by what we had before. In other words, if we sold a lot the day before, that doesn't tell us anything about how much we're going to sell the next day, other than the fact it's normally distributed. It's definitely a strong assumption and not necessarily a reasonable assumption. I know many of you may take odds with that, but usually it's a pretty decent one, especially if you're just trying to get an idea of how things behave and what levels to do to kind of get you in the right ballpark. So just like we had before, when we have a probability distribution of something like that, we can look at S again being the base stock level. It's like how much we carry over the lead time, and that we know that we look at the demand over the lead time. If we look at the probability of the demand over the total amount over the lead time is less than the base stock level, is going to be equal to some probability alpha between 0 and 1. And once again, we're going to call that the service level, or the in-stock probability. It means we don't run out over the lead time. So it's very, very similar to the news vendor model, except for we're talking about over the lead time, and the only thing that's kind of new is that we're talking about repeated things. In the news vendor, it was only one thing, and now we're repeating it over and over and over again, the demand, 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 demand. Okay, so again, you can look at this as the alpha is sort of the probability that the stock is less, the demand is less than our base stock level S, and so it would be the shaded region here. And of course, 1 minus that would be the probability of stocking out, or not having enough, or running out. And of course, the mean is going to be the average demand over the lead time. So let's just take an example. Let's say we wanted to have a service level of 95%, or alpha equals 0.95. Then we would end up wanting to have a safety factor of about 1.65 to hedge our stock over the lead time. So whatever our mean and standard deviation is, we'd want to multiply that standard deviation by 1.65, add that to the average lead, and that would give us the amount of base stock that we should have to maintain a 95% service level, or not stock out. I hope that makes sense. One thing you have to be careful of, as usual, but even more important here, is that the distribution of the demand during the lead time has to be computed in the same time units. Okay, just be consistent about that, because if you're not consistent with the time units, you'll see that things do not calculate the same way, especially now that we're going to be compounding things over a lead time. You'll see that the calculations are going to be way off. So usually companies have statistics on demand in some unit, days, weeks, months, whatever is convenient for them. And so just pick something and make sure that you stay, that your demand, your app, and by the way, we're going to say you're going to use this term AVG for the average demand. And that's not over the lead time. That's just the average demand overall for our product or service, and STD for the standard deviation. Again, maybe that's going to be in days, and that's going to be the variability of the demand for our product period. L will be our lead time. Again, let's try to be consistent and keep them all, say, in days. And whatever you do, just make sure that you keep all your units consistent. Otherwise, you're going to have some rather unpleasant errors in your computations when you look at the base stock level over the lead time. So the question now is, if we have an average demand for our product and a standard deviation, let's say for our product in days, and a lead time, how do we calculate the average demand over the lead time and the standard deviation over the lead time? It's going to be a little bit different than what you might think. So let's take an example. Now, a rule of thumb, the reason why it's different than you might think is because in general there's no way to do this without making some sort of assumptions. So we're going to assume that the demand is normally distributed, and that over the lead time the demand is the same, it's constant and identically normally distributed, and we're not going to, in other words, the demand does not change over the lead time, and that there's no relationship between one day and the next. In such cases, we can add the means, so we can add the average amount per day over the lead time. So if, say, it's 4 days and the average is, say, 10 units per day, then we can add 10 plus 10 plus 10 plus 10, or 40 units a day would be the average over the 4 days. What you can't do is add the standard deviations. And again, this is a little counterintuitive, a little tricky. You just cannot add the standard deviations. Just mathematically, that just doesn't work. Now, if we assume the thing is independent over time, like we have been, then you can add what is called the variances. So the variance, fortunately, is quite simple. You just take a standard deviation and you square it, and then you can add those. And then once you add the variances, you can get the standard deviation by just taking the square root. And that's exactly what we're going to do. In general, just for those of you who are curious, the sum of multiple random variables. So we're talking about looking at the demand for our goods over a period of time, where we know what the demand is, say, per day, and then we want to know what is the demand over 4 days. Well, that would be akin to looking at the sum of multiple independent random variables. And in general, you can't say that the sum of independent multiple random variables are going to be the same distribution as each individual one. So in our case, we're saying that they're normally distributed, and that the sum of independent normally distributed random variables is not going to be necessarily generally normally distributed. Well, actually, in our case, it is. And so for normal distribution, the sum of independent normal random variables is in fact also normally distributed. In other words, the sum of bell-shaped random variables is going to be bell-shaped. But in general, the sum of random variables is not going to have the same distribution as the distribution of the random variables. Imagine, you can think about this in terms of like dice, like when you throw dice. If I throw one die, that has a uniform distribution. Let's say, everything has a probability of 1/6. They're all equal. But if you look at the distribution of throwing 2 dies, that's a sum of one die and another die, that's definitely not going to be 1/12 for everything. You'll see that some things are more probable than others because there's going to be doubles of things, more than one way to add a number up. Any case, yeah, you can think about that on your own, but for us, we're going to be fortunate in the fact that the sum of these things are going to be normally distributed. Okay, so that's going to be useful. So again, let's take a look at an example of 4 days and say the demand is independent of the other days and it's normally distributed, as we assume, for every 1 day, or the demand per day. So let's say the demand per day for our product has an average of 200 units and a standard deviation of 5 units. Then the parameters for the lead time over 4 days would be 4 times 200, because every day we're demanding on average 4 units, and we can add those up. Okay, so that's going to be 800 units over the 4 days, or over the lead time. Now the variance of the lead time is going to be, well, the first thing we need to look at the variance for 1 day, which is 5 times 5, or 5 squared. So the standard deviation is 5, the variance is just the square of that, or 5 times 5. Now those can add, so every day we can add the 25 plus 25 plus 25 plus 25, and we get 4 times 25, which is going to be 100. Now that's going to be the variance over the 4-day lead time to get the standard deviation, and we want that because we're going to look at the normal distribution of the lead time. We take the square root of 100, so we get 10. So notice that if we did 4 times 5, see, the lead time would be 20. The standard deviation would be 20, but you see, you can't just add them. You see the standard deviation is actually only 10. Very, very important that you know you have to add the variances, and then to get the standard deviation, you just take the square root. Now, because the sum of normal random variables is going to be normal, in other words, the sum of the normal random variable for day 1, then day 2, then day 3, then day 4 over our lead time, over the whole lead time, it's going to be normally distributed also, and it's going to have mean 800 and standard deviation 10. And then we can calculate things like what's the probability that our base stock is going to be less than, what is the probability that our demand over the lead time is going to be less than the base stock, for example, which is what we want to do. So if we look at the lead time L in general, then the lead time is going to be normally distributed with mean average, which is going to be the standard the mean for the demand times the lead time, and the standard deviation is going to be the sum of all the variances, which standard deviation squared over the lead time, so that's going to be L times standard deviation squared. And to get the standard deviation back again, we take the square root of that. Simplifying, it's simply the standard deviation times the square root of the lead time. Again, this is where things really get a little confusing. You see, it's not L times the standard deviation, it's the square root of it. So it's always going to be lower. Very interesting, actually. You'll find that's useful. Let's just take another idea. Let's just say instead of having let's just say instead we want optimal, what's our optimal base stock to keep to minimize overages and underages over the lead time. Let's just say we give the service level that we want to maintain a certain service level, say 95%. So let's just say, for example, Home Depot has some SKUs, say store unit, inventory unit, and let's say that there's a supply of 5 days, a lead time of 5 days to get this from, say, another store or something like that, or the main inventory for Home Depot. Let's say the daily demand for that has a mean of 30 and a coefficient of variation of 20%. Now, sometimes it's convenient to give the coefficient of variation, which again is just the standard deviation divided by the mean. So what policy should we have for this SKU that minimizes cost, and we want to maintain a 95% service level? In other words, always have this unit in stock 95% of the time over the time period that we have to order, which is going to take 5 days. So again, we have an average demand of 30 units. Standard deviation is 20% of 30 times 30, because it's the standard deviation divided by the mean. So if we multiply by the mean, we're going to get the standard deviation. So we get 6, and the lead time is 5 days. Once again, we want to make sure that this is 30 per day, 6 per day, and these are in days. So days, days, days. So the average distribution, the average over the lead time is just going to be the sum of the average demand over that lead time. That's 5 days, so it's just 30 times 5. Again, it's this 30 times 5 days, so 150 is what we expect over the 5 days. And the standard deviation, a little trickier. Take the standard deviation, which is 6 days, times the square root of the lead time, which is 5 days. 6 times square root of 5, about 13.42. So if we want a 95% in-stock probability, then, and we're going to assume that over the lead time, because it's the sum of these normally distributed things, that the demand over the lead time is normally distributed with this average and that standard deviation. So we can calculate what amount we'd have to keep on hand to maintain a 95% in-stock probability. Or we want to know that the probability that the demand is less than S over the lead time is the normal distribution with that mean and that standard deviation. So we want to find that S. So the first thing we want to do is find out, well, we want that to be 0.95. We want to maintain that at 0.95. So for that to maintain what S gives 0.95, first we figure out, well, what Z gives 0.95. In other words, what safety factor gives a 0.95 probability, and that would be Z about 1.64. And so if we plug that into our basic conversion from Z's to non-Z's, or basically our stock formula, our news vendor model, it's the same thing. We take our average plus that safety factor times the standard deviation. Okay, 150, 1.64, 1.62, we get 172 units. In other words, we should hold, instead of holding the expected 150, we're going to hold a little bit more. And that's because we want to make sure that we are in stock 95% of the time. Notice that if we wanted to only be in stock 50% of the time over the lead time, we would hold exactly 150. So just like the 9. And if you divide that 172 units by the 5 days lead time, that tells you that, by the average demand 30, there's 30 per day. You'll see that this gives us typically about 8.6 days of demand. So instead of the 5 days of demand, we're going to buffer ourselves by taking a few extra days of demand. Another 3.6. Don't forget that to use the parameters of the lead time and the distribution, and the lead time and the standard deviation over the lead. When you're calculating the base stock, you need to use the average over the lead time and the standard deviation over the lead time. And remember, it's calculated in this funny way because it's compounding over the lead time. Compounding just means it's adding. So in general, the formula for constant lead time would be looking at the average demand times the lead time plus the safety factor times the square root of the standard deviation squared times the lead time. Again, this is going to be the AVGL, and this is going to be the STDL. Now, go ahead and try exercise 1A and 1B. You can take a look at that and see that now you're in the position to try to answer those questions. Here, I'll take a look at that for a second. Let's look at 1A and 1B. So 1A says you have a small fruit stand on campus selling mangoes from the trees in your backyard. You want to bring mangoes from home. You let your spouse know 3 days in advance. Otherwise, you won't get any. So you have to have a lead time of 3 days. L equals 3. Right? And your monthly sales will be 100 mango. Your monthly sales, this is 3 days. Sorry. And your monthly sales will be 1,000 mangoes on average. So AVG, this is the average demand. What we used to call D is 1,000 mangoes a month. Okay, let's just say 1,000 per month, like that. on average, and the price is $4 each. I don't think that's going to matter here. And the standard deviation of 200 mangoes, so STD, but we used to call that just the plain standard deviation, is 200. Standard deviation of 200 per month. So in other words, if this is 1,000 mangoes on month, then this is going to be also 200 per month. Given this uncertainty, you want to make sure you have mangoes 95% of the time. Assume 1 month has 30 days. So, of course, the first thing to do to solve this problem is make sure everything is in the same units. You see, this is in days, and these are in months. So either convert these into days or convert that into months. Typically, it's easiest to convert things into the units for the demand. That's my advice. So in this case, I would say 3 days is equal to 3 divided by 30, right? You can say 3 days, right? And there's, here maybe better to look at like this, times 1 month is 30 days. I like to write out all the units to make sure I'm doing it right. So I take 3 divided by 30, and that would give me that. And then you just plug in your values here. In this case, you don't use this. What you want to do is look at the you want to figure out what z would give the, you have to look at what z, so here I'll put this back here for a second. So you have to say you want the probability that the demand over lead time, that the, not demand over the lead time is less than the stock level S, is equal to, and it said 95%, so 0.95. So that's going to imply that z equals something, and then once you figure that out, you go plug it into here, figure out what this, if we plug it into this actually, plug it into here and here with that z, and boom, you'll have the stock level that you need. 1b is not much different. If you want to look at 1b, you simply, looking at 1b, you're just going to have now some underage and overage. So the space they charge you is 50 units a day, and for every customer walking away without a mango because it's sold, you feel a loss of goodwill 50 a customer. So again, you're going to want to figure out the CU and the CO, right? And this is over the, and then figure out over the lead time, etc., etc., etc. So you're just going to use this one right here. You're going to use this. Okay, figure out what S gives you that. Okay, back to where we were. So again, the base stock level S, typically we have a constant lead time, and as the lead time does not change, like 3 days, is going to be the mean demand over the lead time, okay, calculated as the lead time times the average demand per day, the safety factor, and the square root of the standard square of the standard deviation, which is the variance, times the lead, because those add. Again, we call this the pipeline inventory or the on-order inventory, and we call this the safety stock. Okay, this is the proportionality, but the safety stock, or the safety factor. Okay, so now let's just think about how this might come into play as we're managing our inventory. So we're going to talk about the base stock policy, and the base stock policy means that we're continuously reviewing our inventory and that we are assuming there's no fixed ordering costs. So we're going to assume there's no ordering costs. How would we use this idea on a continuous basis to order enough so that we maintain an economically efficient on-hand inventory over the lead time or a certain service level. So we'll call the inventory position is what is our inventory level at a certain time, and so we're going to call this base stock policy that whenever we drop below our base stock S, that's time for us to order. So this is going to answer when do we need to order, because we're going to continuously monitor our inventory, because remember, it's variable demand, so we don't know exactly when it's going to drop below our baseline base stock level S. But when it does, we're going to, as soon as it does, we want to order enough to bring our inventory level back up to the base stock level, because once it drops below S, then I won't have enough on hand, right, to maintain an inventory over the lead time. So the philosophy here is that you should, as soon as I dip below S, as soon as my inventory dips below my base stock level as calculated by what I need to have to maintain over the lead time, that's time to order and bring it back up to that so that I always have enough to stay in that inventory position. So the way to do that is the inventory position is quite simply whatever I have on hand plus whatever I have on order minus whatever was already ordered by the customers, or there might be on back order. So in other words, I wasn't able to satisfy that, but when it comes in, those are already spoken for. So again, it's what I have on hand plus what I have on order is our inventory position minus what I have on back order, because as soon as those comes in, those are going to disappear and they're no longer going to be able to buffer our inventory. So we call that our inventory position. The policy is to keep IP constant at S units. In other words, we want our inventory position to always be the base stock level S. And again, we calculate the base stock level S in such a way that it's the amount that we need to keep on hand to keep a certain to make sure that we don't stock out over the lead time, or to be economically efficient over that lead time. So again, the policy would be when our inventory position, meaning this inventory position, drops below S, it's time to order some more, enough to bring up to S. So again, when we look at our inventory position, which is the on hand plus on order minus the back order, if that drops below our calculated base stock level S, then it's time to reorder. How much should we order at that point? The amount to bring us back, amount to bring IP back up to S. In other words, the difference between how much we dip below our inventory and the inventory position. So let's just say we have an inventory level on hand is 10, and let's just say our base stock level is 20, and there's 2 units already on order, right? Then we would have an inventory position, and there's no back order, so our inventory position would be 10 plus 2 or 12 units, and so we should order the difference between our base stock level, which is what we want to be at, and what our inventory position is, 20 minus 12, or 8 units. So if we order 8 units, that'll bring our inventory position back up to S. So let's take a look at that more closely. Let's just say that again, at first our inventory position is equal to our base stock level, which is our on hand plus on order minus our back order. Now let's just say that we start with 10, and on the first day we get a demand for 2 units. And then what happens is we're going to look at our inventory, and we're going to say our inventory position should be S, which is 10 units. So again, this is different than the previous example. It's 10 units instead of 20, but we're going to start out with base lock 10. So we have a deficit. Our inventory position is now off by 2. So we're going to order 2 because we want 8 plus 2 to equal 10. That's our inventory position should be equal to our base stock level 10. So we'll order 2. Now we have to wait for us to receive that period of time. Okay, now time goes on and we watch our inventory, and let's say the next day we get a demand for 4 units, or we're monitoring inventory and we have 4 units. Now there's 4 units down. Okay, our inventory now is 4 units, right? So now we have 8 here, but we have now 4 less, so 8 minus 4 is 4. So we now want to order 4 units. Why? Well, again, we want what we have on order plus what we have on hand plus what we've already back ordered to equal our base unit 10. So 4 plus 4 plus the 2 that we already ordered. So we ordered this 2 previously because that's on order. So 4, 5, 6 are on order plus our inventory on hand, which is 4, will equal 10. And so we maintain a stock level of 10 if we order 4. But notice that the inventory on hand is 4. Say the next day we have a demand for 6 units. Okay, good. Now, whoops, we're over our inventory now because we only had 4 on hand. So now our inventory is 0, but we have a back order of 2 because we had a demand for 6. So we're going to have to now order 6 more because, again, we're going to have to look at the sum of what we have on order plus what we have on hand, which is 0, minus the back order. So 6 plus 4 plus 2 minus 2 is going to be 10. Once again, don't have anything in inventory. This is what we have on order. These are what's back ordered. So that's our inventory position. We want that to be 10. Okay, and by the time we get to receiving these things, then our quantity to order will be our actual demand. So that's the way the inventory position, the IP, or the base stock level policy inventory management works. There are other ways to do it, but this is the one if we assume a constant lead time. Well, how does this really work? The uncertainty in a multi-period setting. So we're talking about, in the news vendor model, we really talked about uncertainty only at the time of demand, not over a multiple period of time. So now we're talking about compounding that uncertainty over a period of time, and in particular, we're worried about the lead time. So let's look at the base stock model in comparison to the news vendor model. So what we assume, both of them have uncertain future of demand. Both of them are that we don't know the demand is normally distributed with a certain mean, a standard deviation, but the obsolescence of the inventory in the news vendor we assume happens immediately, so after one period. But in the base stock level, we assume there's no obsolescence at all, that the inventory just stays in there until we need it. Whereas in the news vendor model, if once that period is over, then we're going to have an overage if we have things still in our inventory, or an underage if we didn't have enough. The number of replenishments is 1, or maybe a few if we have reactive capacity, but typically it's a one-shot replenishment. But in the base stock model, we're talking about continuous replenishment. We're always ordering more again and again and again ad infinitum. And that for the news vendor, that during the replenishment period, we just assumed there was no demand at all, like we were at home and we couldn't get the mangoes, so until we come back and sell them the next day. But in the base stock level model, we assume that there is demand over the replenishment period, or in our case, over the lead time. So the news vendor model employs for short life cycle products with uncertain demand, and the base stock model is for long life cycle products with uncertain but stable demand. You can actually combine the two, of course, as we'll see later. Let's take a look at exercise 1C. Exercise 1C says, again, if you have a base stock level of 250 and a group of students come to say they want 100 mangoes tomorrow, and before you leave campus, you look in your refrigerator, there's only 50 mangoes there, and you told your spouse already that you need another 150. Are you going to tell your spouse today that you will need to bring mangoes again, and if so, how many? So the answer is yes, and what you're going to want to do is figure out what the inventory position is. So you're going to figure out what the inventory position is by looking at the at this point, what you have on hand, what there's on order, and what might be customer back ordered, right? And then you're going to order the difference between what your base stock level S is and what the IP position is. So that's the way to answer that one. Now, if the lead time is also uncertain, so far we've been talking about the lead time being constant, but if lead time is also uncertain, then our base stock formula gets modified like this. It's a little difficult to explain exactly why, but you can see what is happening here. So the average, instead of looking at the average lead time as a constant L, we'll look at what the average lead time is as a variable, or lead time as a variable, and we'll look at the average and we'll apply that to the average demand. So this is the average lead time. And okay, so once again we look at the pipeline and the safety stock, and you'll see that the only real differences here are that if the average lead time is just L, you see that that becomes standard deviation squared times L, which is the same as we had before, and average deviation times L, the lead time same we had before. And if the lead time is constant, say it's, that means that the standard deviation would be 0. So this STDL, the standard deviation in lead time, would be 0, and so this would multiply by 0, and so we get the same formula that we had before. So the only difference is if the lead time is uncertain, we use the average lead time and the standard deviation of that lead time, and once again we're also going to assume that the lead time is normally distributed, although that may not necessarily be the case, but you'll find that that works in general pretty well. So the only difference here is we've replaced the lead time with the average lead time. We've added another term representing the standard deviation of the lead time. And okay, so that other term adds the standard deviation for the lead time. So once again, you can see that if the standard deviation of the lead time is 0, meaning that the lead is constant like it was before, this whole thing degenerates into the previous equation. The other thing that we didn't look at is what if the demand is constant? So what if the lead time is variable? It takes us a long time to get stuff, but we don't know exactly when. But the demand is fairly constant, so it could be a product, for example, that's regularly a regular consumable. So that would just be that this STD here is 0, and then you get this thing that degenerates into a formula that we haven't seen, which is very similar actually to the news vendor model if you look closely. One of the things that we think about is that again it gets a little tricky when you think about, well, what is the if the demand is not normally distributed, which is not always a good or at least an accurate statement. In fact, demand really isn't normally distributed from a technical perspective, and sometimes it can be quite far off from that. But even if it is, this turns out to be a rather good approximation. It has to work pretty well. So it's another one of those robust models, like we talked with the EOQ being sort of robust in that you can make a lot of misspecifications. But this one's very robust in terms of the assumptions of the uncertainty in the demand. So let's take a look at an example here. Let's look at Home Depot again. Let's say that the lead time is variable because maybe we have to consolidate with other stores. Let's say the lead time has a mean of 5 days and a standard deviation of 2 days, and that the daily demand for this particular item again is 30 units, and we have the coefficient of variability or variation of 20%, just like we did before. What inventory policy would we want to, given this uncertain lead time, not a constant lead time, if we want to maintain a 95% service level? Okay, once again, we have that our demand is 30 units a day, and our standard deviation would be 6 units a day by looking at 20% times 30, which is again the standard deviation divided by the mean times the mean gives us 6. Okay, days, these are days. And the lead time now is in 5 days, and the standard deviation of that lead time is 2 days. So this is what's new, and we're going to assume that it's normally distributed also. Again, not necessarily a good thing, but to assume, but it does work. Days, 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 and days is important to keep things all in the same units. We want a service level of 95%, which implies that we're going to get a safety factor of 1.64. Again, that's again the probability of stocking out over the lead time is going to be equal to 0.95. The probability of any normal distributed random variable being less than 1.64 is 95%. So then we're just convert this into what we need by using our base stock formula, and boom, we're ready to go. So again, our base stock would be just plugging it into our formula here, except for this time we've got a little more complicated thing. And you work it out, and you'll see that again, see average 30 per day, lead time of 5 per day, safety factor here. Standard deviation of the lead is 2. We have to square it to get the variance. 30 again is the average lead time here, plus 6 squared, which is the standard deviation of the demand, times 5, which is the lead time there. Again, the average lead time. Calculate that all out, we get 251. Again, this is going to be the pipeline stock. This is going to be the safety stock. 251 units. So you notice even at an average lead time, it's actually going to be even more because of the variability in the lead time. So this is going to once again represent the inventory position that we want to maintain. So we could apply the IP stock base stock policy, meaning that anytime we go below the base stock here of 251, we want to reorder to get the stock base stock, or to get the inventory position back up to equaling 251. So we want the inventory position to equal the base stock position at all times. So when there are fixed ordering costs, we'll call that the SS policy. So S would be set to cover the lead time of the little s is going to be, so we call it the little s, big S policy. The should be set to cover the lead time of the demand with the safety stock to ensure we don't stock out over the lead time, so that would be over this part, and that we take big S is to ensure that the fixed costs are optimal, or we call EOQ. So this particular SS policy is going to now incorporate. We already know that our inventory position should be the same as the base stock, but now we want to know what is our overall stock that we should have. Just use the when there are ordering costs. Before we weren't considering ordering costs, but now we're going to consider ordering costs, and so this is just combining it with the EOQ model, as you'll see. So usually what we do for the policy, for the little s big S policy, is that we make an order when our IP drops below the base stock, right, or the reorder point. And how much we should order is, now what we're going to do is we're going to bring our inventory position up to big S. We want to bring it up not to the base stock level, but we're going to bring it up to big S, because that's going to be the more economically optimal position to have if there are ordering costs and holding costs. So we compute the base stock just like we did before, just use the big base stock equation here, and compute the EOQ using the EOQ formula, using the same demand for the overall demand. But just make sure everything is still in the same units. Everybody still needs to be in the same time units. And that would be, again, if you recall, it was just the square root of 2 times the ordering cost times the demand average divided by the holding costs. Let's take the square root of that. So we would set the big S is equal to our base stock plus our EOQ amount. So our EOQ amount is the optimal amount to hold to minimize the holding and ordering costs to balance those out. And the base stock is how much we need to keep over the lead period when it's uncertain. So let's consider how we would do that. Again, look at Home Depot. Let's say there's a fixed ordering cost of about $50 an order, and we assume the holding costs are 15% of the product cost, which is $80 per year. So we assume the store is open 360 days a year, and so we've already figured that the base stock with the uncertain lead time was already 251 units. So we already know the reorder point is going to be 251. Our holding costs are going to be 15% of the $80 a year divided by 360 days a year, so that we get a daily holding cost of $0.0333. $50 is our ordering cost, and our average per day is 30 units demand per day. So we can calculate the Q now, because we got the H and the K. We calculate the Q, we get 300 units. So our EOQ, optimal amount to balance the holding and ordering costs, would be 300 units. So our big S stock level, okay, is going to be the base stock level 251 plus our EOQ, or 551, which seems like a lot, but that's how much we're going to want to have on hand. So we're going to make our inventory position the fact that when do we do this? Now the tricky part here is to remember that the inventory position happens that when we drop below our reorder point of 251, okay, that's when our IP, our inventory position, which is again our on hand, on order minus our back order, drops below 251. Then we're going to order enough not to get to 251, but to get to 551. And again, because that's going to help balance out our holding and our ordering costs. So you'll see that if you can try exercise 1D, it's going to be very similar to this. So in summary, there are different kind of inventory models, but these are the basic ones that we just need to look at. Is our demand or lead time constant? So if we have a demand as constant, we're just going to use our plain EOQ model. If our demand is not constant and there are fixed ordering costs, and there are fixed ordering costs, we can use the base stock, and there are no fixed costs, say that there's no costs at all, we can use the base stock policy. And what we apply it is that when our inventory position drops below our reorder point or our base stock, and we reorder up to bring it up to that base stock level. If there are ordering costs, that means we're going to be subject to holding and ordering costs, so we want to balance those out. So we'll figure out the EOQ, and then when we drop below our reorder point, then we'll order up to the base stock level plus that EOQ. So we're going to end up having more to buffer against. So again, when demand or lead time is uncertain, you're going to just use this more general formula. You can always use this even if the demand is certain and the lead time is certain, because this will just degenerate into the regular news vendor, as you'll see. And so step 1 is to calculate the base stock level. Step 2, if there's no ordering costs, you're done. If there are fixed ordering costs, figure out the EOQ. If there is that, then you can apply the little s, big S inventory management model. So like I said, there are different kinds of inventory policies. These are just some very common and insightful ones. But there are they make some assumptions like we're continuously monitoring our inventory, which may not be reasonable. But there are variations of this that you might hear about, but you get the basic idea from just this. They're all variations of this. So I hope you found this useful, and right now would be a great time to go and try all the exercises. And I will see you in class.